Full-Duplex-Bench, a benchmark to evaluate full-duplex spoken dialogue models on turn-taking capabilities. By Guanting Lin, Jiaqin Lian, Qiri Wang, Gopala Anumanchipalli, Alexander H. Liu, and Hengyi Li. Abstract. Spoken dialogue modeling poses challenges beyond text-based language modeling, requiring real-time interaction, turn-taking, and backchanneling. While most spoken dialogue models, SDMs, operate in half-duplex mode, processing one turn at a time, emerging full-duplex SDMs can listen and speak simultaneously, enabling more natural conversations. However, current evaluations remain limited, focusing mainly on turn-based metrics or coarse corpus-level analyses. To address this, we introduce Full-Duplex-Bench, a benchmark that systematically evaluates key interactive behaviors: pause handling, backchanneling, turn-taking, and interruption management. Our framework uses automatic metrics for consistent, reproducible assessment and provides a fair, fast evaluation setup. By releasing our benchmark in code, we aim to advance dialogue modeling and foster the development of more natural and engaging SDMs. 1. Introduction. Natural spoken dialogue is characterized by complex dynamics. Different from text-based language modeling, spoken dialogue involves problems beyond language understanding for communication, such as turn-taking and backchanneling. These fundamental aspects facilitate mutual understanding, engagement, and social connection. Over the years, spoken dialogue models, SDMs, have become a major research focus, particularly with the rise of voice assistants. Existing SDMs can be broadly categorized into two types. 1. Half-duplex SDMs. These models operate based on a turn-by-turn protocol, processing one audio stream at a time and switching roles in response to turn-changing signals. 2. Full-duplex SDMs. These models can simultaneously listen and speak, allowing them to capture the subtle timing of spoken conversation. They process continuous audio streams and model overlapping speech, pauses, and background noise. Furthermore, these models can capture essential spoken interaction behaviors, such as backchanneling, offering more natural and context-aware responses. Although half-duplex SDMs have been the dominant approach, they often sound less natural than human speakers, who seamlessly listen and speak at the same time. Recent progress in models like GPT-4 voice mode has sparked an interest in full-duplex capabilities for more human-like dialogues. Consequently, many new SDMs have emerged, with different architectures to enable real-time communication. As an increasing number of these systems are proposed, fair and open evaluation is critical to guide future advances in spoken dialogue research. Figure 1. Overview pipeline of Full-Duplex-Bench. We feed user audio streams to a full-duplex SDM, which produces time-synchronous output. We then perform post-processing to align both streams at the transcript level, enabling automatic evaluation along multiple dimensions. Evaluating SDMs is challenging because human conversation requires understanding a wide range of information and interpreting complex interactions within speech signals. Previous benchmarks have largely focused on three areas: content-based evaluation, measuring performance on tasks such as spoken question answering, instruction following evaluation, assessing a system's ability to follow directives, and paralinguistic evaluation, examining factors like emotion or speaking style. However, these benchmarks mostly assume turn-based interactions, leaving the real-time aspects of full-duplex models underexplored. Table 1. Overview of full-duplex speech-language models. Blank indicates properties that are not publicly available or unspecified. E2E denotes end-to-end speech modeling without relying on text. Hash indicates the number of speech input channels. Interrupt refers to interruption handling. BC represents back-channeling capability, and S2S release shows whether the complete speech-to-speech pipeline is publicly released. Recent studies attempt to evaluate interaction timing in full-duplex dialogue. DGSLM examines voice activity patterns by comparing model outputs to ground truth gaps, interpausal units, and pauses. However, the corpus-level statistics are difficult to interpret, and the ground truth is based on a specific dialogue dataset. Recently, Talking Turns trains a specialized judge model to evaluate alignment with conversational behaviors. However, this model is trained on a specific dialogue dataset, which may limit its generalizability to other dialogue types. Moreover, the evaluation relies on user studies, making the results difficult to reproduce due to variations in participants. While these works provide valuable insights, They highlight the need for a more unified and reproducible approach to evaluating full-duplex SDMs in real-world scenarios. In this paper, we present Full-Duplex-Bench, the first scenario-driven benchmark for systematically evaluating key turn-taking behaviors in human-to-machine full-duplex spoken dialogue models, SDMs, as illustrated in Figure 1. The benchmark evaluates models under realistic conversational events such as backchannels and user interruptions, focusing on 4 critical aspects of real-time interaction: pause handling, backchanneling, turn-taking, and user interruption management. Our unified framework offers objective behavior detection, rapid diagnostic metrics, and an open, reproducible toolkit, enabling consistent and reliable cross-model comparisons. The metrics are intentionally descriptive rather than prescriptive, allowing developers to prioritize behaviors according to specific application requirements. Designed for efficiency and full automation, the benchmark supports rapid large-scale evaluation and provides deeper insights into how existing systems manage interactive dynamics in real time. We publicly released the benchmark and codebase to facilitate further research and the development of more engaging and conversational SDMs. 2. Related works. A. Full-duplex spoken dialogue models. Recent advances in SDMs have increasingly focused on full-duplex capabilities. We categorize existing full-duplex SDMs into 2 main groups: transparent models, which offer a detailed architecture and implementation, and closed-source commercial systems, which are accessible only through demos. Table 1 summarizes the key properties of these models. Transparent models. These models are publicly available with open-source implementations or detailed technical descriptions, enabling reproducibility and deeper analysis. They fall into 2 subcategories: cascaded models. These systems follow a modular pipeline structure, typically integrating ASR, LLM, and TTS components. Wang et al. 27 introduce control, speak, and listen tokens in an LLM framework with perceptual pulses. MiniCMP Duplex and Mimic PM Duo apply time-sliced token windows for synchronous dialogue modeling. Vita and Freeze Omni operate on raw speech inputs, improving latency while maintaining internal reliance on text. While cascaded approaches offer flexibility and stronger semantic modeling, they often suffer from cross-module latency and the loss of nuanced speech features, driving growing interest in end-to-end alternatives. End-to-end models. These models jointly model speaker and listener audio streams. DGSLM26 employs a Siamese network with cross-attention for 2-channel dialogue. Moshi 2 uses parallel processing streams to handle real-time user speech and supports overlaps and interruptions. Synclum LM16 introduces time-synchronous audio chunk modeling for 2-channel speech. OmniFloat 32 flattens and processes speech and text tokens jointly. Salmono Multi 31 and MinoPM 30 inject state tokens to improve turn-taking modeling. Parrot 29 predicts next token pairs across streams, while RTTL-DG 33 uses a dialogue manager to control generation timing. By operating directly on audio data, end-to-end approaches have the potential to capture a wider range of speech features, including paralinguistic and nonverbal cues, as well as dialogue behaviors such as backchanneling. Closed-source commercial systems. Several commercial models have demonstrated full-duplex capabilities through public demos. These systems, such as GPT-4 Voice Mode, Gemini Live, Dubao, and Novasonic, are not open-source and lack publicly available architectural details. Nonetheless, we include them in Table 1. Their emergence underscores the need for open and standardized benchmarks to evaluate interaction quality across both transparent research models and proprietary commercial systems. B. Evaluation benchmarks. Benchmarks offer a common framework for comparing models and understanding their performance. In the speech community, several benchmarks have been proposed to evaluate specific aspects of speech models. The Superb series tests self-supervised speech representations across a variety of tasks. Recent advances in universal spoken language models have resulted in benchmarks that evaluate both understanding and generation. These can be grouped as follows. Multitask instruction following, Dynamic Superb, Voice and Bench, and Air Bench test a model's ability to perform a range of tasks based on specific instructions. Semantic understanding. For low-level language skills, such as syntax and semantics, benchmarks like Zero Shot and Spoken Squad have been introduced. Higher-level comprehension, including spoken question answering, is measured by benchmarks like Llama Question and Spoken Web Question. Paralinguistic perception, Vox Dialogue, SD Eval, and Style Talk evaluate the ability to produce natural responses by considering features such as emotion, gender, and accent. Talking Turns trains a judge model on a specific dialogue dataset to assess conversational alignment, but its generalizability is limited. Its reliance on user studies also hinders reproducibility. These limitations highlight the need for a unified, reproducible framework for evaluating full-duplex SDMs. To this end, we propose a benchmark with an automatic evaluation pipeline and behavior-specific metrics for assessing conversational performance. 3. Full-Duplex-Bench framework. For clarity, we first defined several key terms that will be used in this paper. Backchannel. In natural conversations, listeners often provide short verbal or nonverbal signals, known as backchannels, to indicate active engagement and understanding. These backchannels include utterances such as mm-hmm and uh-huh, which typically occur while another person is speaking. Effective backchanneling enhances conversational fluidity by signaling attentiveness without disrupting the speaker. Generally, backchanneling refers to short utterances produced by the listener while the speaker is talking. In this work, we classify a speech segment as backchanneling if it meets the following criteria. 1. It has a short duration of less than 1 second. And 2, it contains fewer than 2 words. This ensures that speech is delivered at a reasonable pace and that brief utterances do not interrupt the current speaker's turn. The concept of backchanneling differs across the literature, so developing a comprehensive detector is beyond the scope of this paper and is left for future work. Takeover. A takeover occurs when the model effectively assumes control of the conversation, dominating the turn and granting minimal opportunity for the user to speak. In this work, takeover is treated as a binary variable. If the model merely responds with silence or a backchannel, no takeover is deemed to have occurred. Conversely, any other non-silent speech that is not a backchannel indicates the model's attempt to take over. Formally, TO equals 0 if silence or backchannel, 1 otherwise. Takeover rate, TOR. To quantify how often takeovers occur, we define the TR as the average value of the binary TO variable across the dataset. TOR equals the sum of all TO sub I over n, where n is the total number of dialogue turns, and TO sub I is the binary takeover variable for sample I. A. Overview. As illustrated in Figure 1, our framework employs a unified speech input to simulate real-time user interactions with SDMs, enabling detailed evaluations across various dimensions. For each aspect, we design targeted test samples, collect the model's speech responses, and use an ASR model to produce word-level, time-aligned transcriptions. Dedicated metrics are then applied to assess performance in each dimension. B. Evaluation dimensions. Figure 2 illustrates the following 4 evaluation dimensions. 1. Pause handling. Humans naturally pause and hesitate during conversations. Pauses can occur between consecutive turns or within the same sentence. These pauses are often not intended to yield the turn, but rather to maintain control of the conversation. Therefore, taking over the turn during such pauses is undesirable and may lead to user dissatisfaction. Effective pause handling ensures that the model does not interrupt when a speaker takes a natural pause. Research question. Can the model recognize when the other speaker is still holding the turn and understand that it should not take over? Figure 2. Illustration of the 4 evaluation dimensions in Full-Duplex-Bench. 1. Pause handling. The model stays silent during user pauses. 2. Backchanneling. The model offers short, timely acknowledgments. 3. Smooth turn-taking. The model takes the turn in time. And 4. User interruption. The model handles sudden user input with appropriate, well-timed responses. Metric. The ideal model behavior is to avoid taking over the turn while the user is speaking. To evaluate this, we use the takeover rate, TOR. A lower TOR signifies better pause management, indicating that the model effectively waits for the user's turn to end. In contrast, a higher TOR suggests that the model is more likely to take over the conversation before the user has yielded the turn. 2. Backchanneling. Drawing on the definition in Section 3, we assess whether the model, when interacting with a dominant speaker, actively listens and provides backchannels at suitable moments to facilitate dialogue engagement. A model exhibiting human-like backchanneling behavior should respond at the right times and with an appropriate frequency. Research question: can the model determine when to offer back channels in a human-like manner without interrupting the speaker? Metric: to measure how well the models generate back-channel cues, we use 3 metrics: takeover rate, TOR. As with pause handling, the model should avoid dominating the turn, so a lower TOR is preferable. Back-channel frequency, freq. Each back-channel event is counted and normalized by duration, events per second. When the model does not take over the turn, TOR equals 0. A higher back-channeling frequency indicates that the model responds back-channel more often, but this does not necessarily imply better or more natural behavior, as it also depends on timing and context. Jensen-Shannon divergence. This captures the difference between the model's predicted timings of back channels and actual human timing. The model outputs a probability distribution P, where P of I denotes the likelihood of a back channel occurring in time window I. The ground truth distribution Q is derived from human annotated back channel timings, details in 3C, aligned to the same set of time windows. To measure the similarity between P and Q, we compute the Jensen-Shannon divergence, JSD, as JSD of P and Q equals 1/2 sum over I P of I log P of I over M of I plus Q of I plus 1/2 sum over I Q of I log Q of I over M of I, where M of I equals half P of I plus Q of I and I indexes the discrete time windows. JSD ranges from 0 perfect alignment to 1 complete divergence, providing a symmetric and bounded measure of similarity between model predictions and human back-channel behavior. We only calculate this metric when the model does not take over the turn, where each back-channel event is counted as one hot and normalized into a probability distribution. If the model stays silent throughout, we assume a uniform probability distribution, treating it as a random baseline without back-channel knowledge. 3. Smooth turn-taking. Effective turn-taking is crucial for maintaining a natural and engaging conversation. In human dialogue, smooth turn transitions occur when speakers respond promptly without excessive delay or overlap. A well-designed model should be capable of recognizing turn boundaries and responding with appropriate timing to ensure fluid interactions. Research question: can the model detect the end of a speaker's turn and respond promptly without long pauses? Metric: we measure the averaged response latency, the time in seconds between the end of the user's speech and the start of the model's response. Lower latency values indicate smoother turn-taking. In cases where the model fails to respond, we record the TOR. The latency is calculated only when TOR equals 1. This avoids averaging with non-takeover periods, which would introduce significant variance due to periods of silence. 4. User interruption. In human conversations, interruptions are common and can occur when a listener interjects mid-turn to clarify, disagree, or shift the discussion. A well-designed conversational model should be able to recognize and adapt to such interruptions by adjusting its response appropriately. Effective handling of interruptions ensures that the model remains responsive and coherent, even when the dialogue flow is disrupted. Table 2. The number of samples for each dataset and task. Research question: can the model detect and adapt to user interruptions while maintaining a coherent and timely response? Metric: the evaluation consists of 3 measures. TOR. TOR is measured to ensure the model takes the turn following an interruption, ideally TOR equals 1. The below metrics are calculated only when the TOR is 1, GP-4. Score. A large language model evaluates the quality of the system's response coherence, relevance, and adaptability on a scale from 0 to 5. Higher scores indicate better performance. Latency. After interruption. The average time taken for the model to respond after an interruption, with lower average latency indicating smoother interaction. C. Data curation. The overall evaluation set of Full-Duplex-Bench is shown in the Table 2. We explain how we collected the data for each evaluation dimension as follows: Candor pause handling, Candor smooth turn-taking. We use Candor 43, an 850-hour dataset of open-ended, spontaneous speech conversations with 2-channel recordings as our primary data source, to construct suitable data samples for our benchmark. For the pause handling task, we first apply voice activity detection to identify segments with no overlapping speech, ensuring that only one speaker is active. We then select turns containing an internal pause between 0.4 and 1.0 seconds. This range is informed by prior research showing that pauses around 1 second are perceived as a natural upper bound in English conversation, and that pauses within this range can influence listener impressions. We exclude turns shorter than 5 seconds and remove cases where the speech immediately before or after the pause consists of back-channel responses. For the smooth turn-taking task, we compute the gap between each pair of consecutive turns and retain only those where all gaps are less than 0.4 seconds. This threshold is based on findings that smooth conversational transitions in English typically occur within 250 to 250 milliseconds, and we conservatively set 0.4 seconds as an upper bound. We further require no overlapping speech, each turn to be longer than 4 seconds, and that the utterances are not back-channeling. To give evaluated models sufficient time to respond, we appended 5 seconds of silence at the end of the input stream. After automatic filtering, all retained segments are manually reviewed with dual-channel evidence, whether the partner is silent or entering, and whether there is hesitation or fluent continuation. ICC, backchannel, Umair et al., use the in-conversation corpus ICC to collect transition relevance places, TRPS, which are points in a speaker's utterance that signal appropriate moments for the listener to respond. This dataset consists of 28.33 hours of high-quality, informal American English dialogues, capturing responses from 118 native speakers with no prior expertise in turn-taking research. Participants were instructed to provide brief back-channel responses, for example, and yes, whenever they found it appropriate. Their responses were recorded on individual audio channels, synchronized with the stimulus audio. On average, 59 participants responded to each stimulus turn. This allows for estimating both the likelihood of perceiving a TRP at a given moment and the distribution of these perceived response locations. By segmenting the audio into 200 milliseconds time windows and normalizing the back-channel counts, we generate a ground truth back-channel distribution queue for computing JSD for each stimulus. Synthetic data, user interruption, pause handling. To address the scarcity of user-wrapped interruptions in existing public datasets, we generated synthetic dialogues using GPT-4.8, which include both contextual turns and interruption turns. Text-to-speech synthesis was performed using Chat-TTS, with 10 different speaker voices randomly assigned across samples to enhance diversity. For each input stream fed to the evaluated model, the interrupting speech is played around 7 seconds after the preceding utterance. Additionally, we append 15 seconds of silence after the interruption to allow the model time to continue its user-friendly interface. 4. Models under evaluation. Since many models do not release complete speech-to-speech checkpoints, currently we evaluate models with a publicly available speech-to-speech model and inference pipeline. We also include the recently released Gemini Live API as a representative commercial model due to its user-friendly interface. DGSL. A textless speech-to-speech model that generates natural conversations directly from audio. It uses a Hubie ERT plus K-means encoder, a dual-tower transformer for 2-channel dialogue modeling, and a hi-fi GAN decoder. Trained on 2,000 hours of phone calls, it captures both linguistic and paralinguistic cues. Using their demo non-interactive, we adapt it for live interaction using the official implementation with our modifications. Moshi, a real-time speech-to-speech system combining a 7BLLM, helium, and neural codec, MIMI, via residual vector quantization. It features an inner monologue step to improve fluency and supports overlapping speech and does interruptions through a multi-stream architecture. We use the official implementation. Table 3. Models comparison. We evaluate several models across different conversational dimensions where latency is presented in seconds. Freeze Omni, a cascaded full-duplex system with a frozen LLM pipeline. VAD triggers chunk-wise encoding, and a classification head predicts dialogue states to control turn-taking. Parallel modules handle streaming, speaking, and monitoring, evaluated locally using the official server. Gemini Live. Based on the official API documentation, we use the Gemini 2.0-Flash-Live 2001 model. Here, the audio is first converted to 16 kHz PCM16 format, then divided into 30 milliseconds chunks and streamed to the Gemini Live API. Server-side voice activity detection is used to segment the audio and trigger responses. A new session is initiated after each model reply. All generated outputs are aligned with the original input duration, preserving silence in regions where no response is required. 5. Results. Table 3 presents various scores for evaluation dimensions. The key findings are summarized as follows. Avoiding interruptions during speaker pauses. All 3 SDMs exhibit high takeover rates during longer natural speaker pauses, indicating frequent interruptions during manual breaks. The end-to-end models tend to interrupt more often across both real and synthetic datasets. In contrast, Freeze-Omni, which incorporates a dedicated module for predicting speaking and listening states, demonstrates a significantly lower takeover rate. This suggests that an explicit turn-taking control module can better manage pauses and may offer improvements if integrated into end-to-end systems. Conversely, Gemini Live achieves the lowest takeover rate among all models, including open-source ones, and exhibits a higher likelihood of taking over on Candor compared to synthetic data. Backchanneling dynamics. We evaluate using takeover rates, backchannel frequency, and Jensen-Shannon diversity. Similar to pause handling, Moshi frequently takes over the turn, resulting in a high takeover rate. Both DGSLM and Freeze-Omni achieve lower takeover rates. Among the 3 open-sourced SDMs, DGSLM produces the most backchannel responses with more natural timing when it does not take over the turn. In contrast, Freeze-Omni remains largely silent, producing few backchannel responses. The commercial Gemini Live achieves the lowest takeover rate and the best Jensen-Shannon diversity, indicating superior ability in identifying appropriate moments for backchanneling. Latency of turn-taking. We assess takeover rate and average response latency on the Candor dataset. DGSLM and Moshi exhibit high takeover rates and respond quickly, with an average latency of around 0.3 seconds. Freeze-Omni, due to its cascaded architecture, which first generates text and then synthesizes speech, exhibits higher latency. Its lower takeover rate likely reflects missed opportunities to take over the turn, possibly due to failures in detecting turn ends. Interestingly, Gemini Live achieves a takeover rate of only 0.655, suggesting that even commercial models sometimes fail to take the turn in real dialogue data. Managing user interruptions. Freeze-Omni handles user interruptions effectively, achieving significantly higher contextual response scores while maintaining acceptable latency. This strength is attributed to its model-as-a-server strategy, which leverages a pool of models to manage user margins efficiently. Gemini Live shows comparable performance, with relatively better takeover rate and latency, though it yields a slightly lower score. In contrast, the end-to-end SDMs struggle with unfinished content quality compared to having GPT-4 score. These results highlight the challenges end-to-end systems face in preserving semantic coherence during user interruptions. 6. Conclusion. In this paper, we introduced Full-Duplex-Bench, a benchmark designed to evaluate critical aspects of full-duplex spoken dialogue models. Our framework targets key interaction dimensions: pause handling, backchanneling, smooth turn-taking, and user interruption management, addressing limitations of existing benchmarks that primarily focus on half-duplex settings or coarse corpus-level metrics. To ensure systematic and reproducible evaluation, we propose automatic metrics tailored to real-time interaction. Experiments on full-duplex models reveal distinct model features and highlight areas for improvement. By releasing our data and behavior-specific metrics, we hope Full-Duplex-Bench provides a practical foundation for evaluating full-duplex spoken dialogue systems. 7. Limitation and future work. Our framework does not yet link described behaviors to human preferences. Users need to determine what constitutes desirable or undesirable behavior according to their specific goals. Future work can integrate human judgment studies to provide the preference. The present analysis is limited to English, and extending the framework to other languages will be essential for assessing cross-linguistic generality. This concludes the reading of Full-Duplex-Bench, a benchmark to evaluate full-duplex spoken dialogue models on turn-taking capabilities on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.